All right, so here we go. Now, something that was probably introduced to you in Gen Chem, but we're going to go into it with much more depth in organic chem is the idea of resonance. Okay. So resonance forms, if you remember, or if you don't, it stems from the idea that a lot of molecules cannot be represented with just a single Lewis structure. Okay. There's not a single representation that is only dogmatically correct. There may be a few that are also just as legitimate. So some molecules have structures that cannot be shown with a single representation. So what you do is you write multiple ones. And so they're represented by structures that contribute to the final structure. But how they differ is they differ in the arrangement of pi bonds, so multiple bonds, double or triple bonds. They differ in the position of the pi bonds and or lone pairs of electrons. Okay, so resonance forms are represented by structures that contribute to the final structure, but differ in position of the pi bond or lone pair. Okay, so you can see there from the example that you've got illustrated here. Why was the double bond drawn between the carbon and the oxygen above? Why not draw it down below? Well, that's just as legitimate. Okay, so these are two resonance forms of the acetate ion. The double bond could be between the carbon and the oxygen up top, or it could just as legitimately be drawn with the carbon down below. Okay. Here's one important thing. All atoms have to stay in the same location. If an atom moves, it's not a resonance form. What you drew could exist, but it's just not called a resonance form. We'll get to what that's called later in the course. But all atoms of resonance forms stay in the same location. The only thing that moves would be a multiple bond and or a lone pair of electrons. Okay. So resonance hybrids then. Resonance hybrids are where you take all the resonance forms and you kind of smash them together to be what really represents the structure of the molecule. And the way that we kind of explain that in the notes here in this bullet, this is a structure with resonance forms, but it doesn't alternate between the forms. So a hybrid is kind of a mixture of all of the various resonance forms. So this is a structure with resonance forms that does not alternate between the forms. All right, and a good example of this is benzene, which has the formula of C6H6. It has two resonance forms where you have that alternating double and single bonds. So a good example of a resonance hybrid is benzene. C6H6 has two resonance forms with alternating double and single bonds. And here's a picture. Okay, so you can see from this structure written on the left here, the double bond is right there. Okay, but in the one right next to it, all you did was you just replace that with a single bond and just shifted the double bond down one. Okay, the alternating double bond, single bond, double bond, single bond, double bond, single bond. Well, it could be single bond, double bond, single bond, double bond, single bond, double bond, right? They're equivalent. So these are two different resonance forms. But in reality, what you have is a hybrid of those two, and that's represented a couple ways, what you see on the right. Many times you'll see the benzene ring with a circle in the middle, and sometimes the circle is even a dashed line. Okay, and that's just to show you that really it's a mixture of the two resonance forms. Okay, and so the hybrid is a average, or really more specifically, it's a weighted average of the two individual forms. And it turns out that in benzene, the reason why we know this is because we know from experiments that all 6 of the carbon-carbon bonds in benzene are equivalent to the same length. It's not like some of the bonds are shorter than the other bonds. They're all the same length. It's a perfect hexagon. So that's how we know that it's not really double bond, single bond, double bond, single bond. We know that it must be some sort of hybrid, a mixture of the two. Okay. All right. So another one that, again, hopefully you've seen maybe back in Gen Chem is carbonate, CO3 2-. Well, in the first resonance form on the left there, that double bond occurs between the carbon and the oxygen up top, but why? Why didn't we write it between the carbon and the oxygen on the left? Well, you could do that. That's another resonance form. And that follows that we could also write the double bond between the carbon and the oxygen on the right. So that's another resonance form. So the hybrid then is just a mixture of all three, is an average of all three of these. And so that's where you get that Lewis structure that's in your handout there that shows that it's not really a double bond anywhere. It's 1 1/3 bond. That extra bond gets kind of smeared out over all of the ion. And the charge, that charge of -2 gets smeared out, divided up amongst the 3 different oxygens. Okay. And again, the reason why we know this is because they did some experiments and they determined that in actual carbonate ions, the carbon-oxygen bonds are all the same length. You don't see one of them being shorter than the other. They're all the same length. And so they also have the same bond order. And that means also that each oxygen has a negative 2/3 charge. Okay, so to kind of recap, those individual resonance forms are actually imaginary. They're not real. Okay, the real structure is the hybrid. Now, coming up with those individual resonance forms help us understand the hybrid. That's true, but they're not real. They are imaginary. The real structure is the hybrid. And this is, again, one of those advantages the molecular orbital theory has over valence bond theory. But it's, we don't get into it in this lesson, but I have the picture on the right that you can see that when you do molecular orbital theory on benzene, you can see that there is a molecular orbital that electrons are in down here that covers all 6 carbons. So, there's a pair of electrons that are shared equally among all 6 carbons. They're not isolated between 2 of the carbons. They're smeared out over all 6 carbons. And that's true of these other higher energy molecular orbitals as well. So all right, so I already kind of talked about this with the example, but there are some rules for doing resonance forms. First of all, they don't have to be equivalent. If you can draw multiple resonance forms, they don't have to be equivalent. Okay, different resonance forms of a substance do not have to be equivalent. They don't have to be exactly the same. All right, so what that means is some of them are going to be better than others. Some of them will be major contributors and others minor contributors. So there may be major contributors and minor contributors. Okay. When this is the case, when 2 resonance forms are non-equivalent, the actual structure, remember we said that the individual resonance forms don't accurately describe reality. It's a mixture, it's a hybrid. And so the actual structure of the hybrid mostly resembles the most stable form, the more stable form. Okay, so when 2 resonance structures are non-equivalent, the actual structure of the resonance hybrid mostly resembles the more stable form. Okay, so let me talk about that. That's pretty abstract. Let me give you an example. Oh, actually, I want to give you this list of rules first, and then I'll give you an example. So one of the rules that has to be obeyed is the normal rules for valency. In other words, the octet rule. I say it that way, the normal rules for valency, is because remember that hydrogen doesn't obey the octet rule. Hydrogen's happy with just 2. All right, another important one, key one, is that the major contributors are going to minimize formal charge. Remember, capital F, capital C, that's what we use to abbreviate formal charge. So major contributors usually minimize formal charge. So there will be some situations where minimizing the formal charge means everybody has a formal charge of 0. But there will be other situations where you can't get all of them to have a formal charge equal to 0. Some of the atoms will have a non-zero formal charge. And so when that's the case, when the formal charge does not equal 0, the most electronegative atom should have the negative formal charge. And the least electronegative atom should have the positive formal charge. Okay, so we put negative charges on very electronegative elements. We put positive charges on relatively, smaller electronegativity valued elements. Okay, and just another point that we've said before, but just to get it in the notes once again, is that the importance of resonance is that it leads to stability. When something has resonance, generally it means it's going to be more stable. Resonance affects the properties of the compound and generally increases stability. All right, so we have isocyanate ion, OCN-. So down below you see, and it's already printed in your handout there, the 3 resonance forms that can be drawn. So what we want to do is we want to pick out which one is the major form, which one is the minor form, and is there one that's just not even realistic? So here we go. So first of all, we can say that in structure 2, what we've done is we've minimized the formal charge, and we followed the rule that says you put the negative formal charge on the most electronegative element. So it's the most stable. So number 2 here, okay, because the negative formal charge is on the oxygen, right? And we're obeying the octet rule. And we've minimized formal charge. Now, what do I mean by minimized formal charge? We'll look over here at number 3. Number 3, you have not minimized formal charge because you got something with a -2 formal charge on it right there, okay? And that's really far away from 0. That's not realistic. Nature will want to minimize these formal charges. And then we've got a plus formal charge in this oxygen, and oxygen's a really electronegative element. So that's also destabilizing. So that's what we're going to say in the next bullet here. Okay, that structure 3 is least stable because it does not minimize formal charge across the structure, and because it puts a positive formal charge on an electronegative atom, oxygen. Structure 3 is least stable because it does not minimize formal charge across the structure, and because it puts positive formal charge on an electronegative atom, oxygen. Okay, so what that means is the outcome, the result is that the resonance hybrid would resemble structure 2 the most. That's going to be the major contributor. So the resonance hybrid will resemble 2 most, major contributor, with some properties of 1. 1, there's nothing really, number 1 isn't violating any rules except for it puts that formal charge. You notice that it does put the formal charge, that negative formal charge, on nitrogen. Okay, right? And oxygen is more electronegative than nitrogen, but nitrogen is one of those elements that's pretty electronegative. So it's going to contribute some, but it's not going to be the major contributor. This one is going to be the major contributor. This one is going to be the minor contributor. Okay, and 3 is probably going to be a non-contributor. Oops. Because it violates rules all over the place. It does not minimize formal charge. It puts positive charge on an oxygen, which is not a good idea, and so forth. Okay. All right, so the skill that you need to develop then is to be able to not only draw resonance forms, but identify which ones are going to be the major contributors to the resonance hybrid versus minor contributors, and so forth. Okay. Okay. So what we're doing then, remember, is that we're just differing the position of multiple bonds in lone pairs. Okay. And the way we represent that change is with the notation is called curved arrow. So a curved arrow indicates the movement of electrons, not of the atoms. And you'll see what I mean by that is that when you see these curved arrows written out, we're not saying atoms are moving. We're saying that electron pairs are moving. Okay. And the other name for this is pushing electrons. And I just point that out because it's not in your textbook, but if you're watching like a YouTuber or something, that may be the phrase that they use. That's what I learned, again, back when dinosaurs roamed the earth, and I learned this stuff. So I learned it as being called pushing electrons. Okay, so now let's just get some practice. I'm going to demonstrate here, and then we're going to go back through our handout, and we're going to push electrons with this curved arrow annotation. Okay, so we're going to show with arrows what's going on with these. So look at the difference between these two resonance forms. What has happened is that one of these bonding pairs right here has gone from a bonding pair and become a lone pair. So that's the curved arrow way of showing that. When you have a bonding pair becoming a lone pair, you draw it from the bond to the atom that it's going to. So notice the difference here. This oxygen, this pink oxygen, has 2 lone pairs on the left, but it has 3 lone pairs on the right. So where did that third lone pair came from? It came from this multiple bond. One of these bonding pairs became a lone pair. Okay. Well, what happened to the green oxygen down below? Well, it had 3 lone pairs, and now it only has 2 lone pairs. So what happened was one of these must have become a bonding pair. So I just draw the arrow from the lone pair to the bond. And you can see that what was a single bond on the left becomes a double bond on the right. Okay. So that's what I mean by, pushing electrons or using the curved arrow notation. And you could have drawn in the opposite direction if you wanted to, but you pick one to draw on. Okay. All right, so now let's do, I think the next one in your handout there was the benzene. So let me show you how to do that one. Okay, so, well, what's the difference between these two resonance forms? Well, it's the position of the double bonds. So in this case, a double bond is not becoming a lone pair, it's just changing place. So the way you show that is you just draw where it goes. So it went from there to there. And this one went from there to there. And this one went from there to there. Okay. So that's how you would show the curved arrow notation for when it's not lone pairs becoming bonding pairs or bonding pairs becoming lone pairs. It's just the multiple bond switching places. That's how you represent that. Okay. And then the next one in our notes that we can draw on is that with the carbonate. Okay. So once again, we look at the difference between like the one on the left and the one in the middle. So what has happened? Well, this single bond becomes a double bond. So one of these lone pairs becomes a bonding pair. So I draw that. And then this double bond one of these bonding pairs becomes a lone pair. So I draw an arrow like that. So here, a lone pair becomes a bonding pair. There you go. And here, a bonding pair becomes a lone pair. There you go. And we could do the same thing over here. Okay. So in this case, this, there's a couple ways of showing this. So this lone pair of electrons can become a bonding pair. Okay. And then this bonding pair becomes a lone pair. So again, that leads to a double bond over here and a single bond with 3 lone pairs on the left there. Okay, so hopefully you're getting a feel for how to do this, this curved arrow notation on drawings. Okay, one more. And I didn't put all 3 of the resonance forms for the isocyanate simply because one of them we said wasn't realistic anyway. And so what's the difference? Well, this is a bonding pair. It's a double bond, but it becomes a single bond. So that means that one of these becomes a lone pair. Okay. And then one of these lone pairs on this nitrogen right here becomes a bonding pair. So it goes from a lone pair to a bonding pair to turn that double bond into a triple bond. Okay, so that's how you could annotate the isocyanate problem with curved arrows. Okay, now let's throw a reaction in there because a lot of times these resonance forms don't show up until we carry out a reaction. So it's what we labeled post-reaction resonance. So many times the mechanism of a reaction will depend on the presence or absence of resonance in an intermediate product. Okay, so whether or not a reaction really proceeds forward or the rate at which it proceeds forward many times just depends on the presence or absence of potential resonance forms. Okay, many times the mechanism of a reaction will depend on the presence or absence of resonance in an intermediate product. Okay, so the example here that we've got. So this is just a reaction where we remove a hydrogen, like a strong base comes along. So if we have a strong enough base, I'm just going to represent that with a B. So I have this strong base comes along and pops off that hydrogen. So then, that leaves a lone pair of electrons on the carbon. That's what this lone pair is here. Well, there's resonance associated with that. That can become a bonding pair, and then it can push that one of these bonding pair electrons up on the oxygen to make it a lone pair. And so because of that resonance, these 2 resonance forms, that actually stabilizes this intermediate a little bit. Okay. So that's what we mean by this, it having an impact on the reaction mechanisms. Okay. Now in this case, if we were to label which one is the major, which one is the minor, we would label that resonance on the right as major. And the reason why, of course, is because oxygen is more electronegative than carbon. So we know that the reality, the resonance hybrid, is going to be more like that resonance form than the other one. That's the minor form. It's legitimate because everything obeys the octet rule. And it's this, sort of the gateway into this intermediate because you got to pop that hydrogen off of the carbon. But it's going to be a minor contributor because carbon is less electronegative than oxygen. So it's not going to want that negative formal charge. Okay, so far we just dealt with the negative formal charge. What do you do with a positive formal charge? It's a little different in that what you see is that the second bond, the pi bond, it just jumps over an atom. Okay, so you can see that there in the diagram. That when you've got a positive formal charge jumping around in resonance forms, that second bonding pair of electrons just jumps over an atom. Okay, so we have the double bond between the carbon on the left and the central carbon, but on the other resonance form, it's between the carbon on the right and the central carbon. And the consequence of that is that this positive formal charge went from the carbon on the right to the carbon on the left. And the same thing happens when you have a free radical, an unpaired electron. Okay, it behaves the same way as a positive charge. Radicals have an unpaired electron and they behave the same way as cations, as positively charged ions. All right, so we need to finish up with a discussion on delocalization. So another way of describing resonance forms is you're delocalizing the electrons. The electrons are not centered on one atom or between 2 atoms in a bond. They kind of get smeared out over a larger part of the molecule. That's delocalization. And that leads to increased stability. So resonance leads to increased stability because it delocalizes the electrons around the structure. So remember that, the more positively charged nuclei that the electron pair can be attracted to and influenced by is going to lower the energies of those electrons. So that's why it stabilizes it. That's why delocalization stabilizes the electrons, because there's more positively charged nuclei that it can interact with. Okay. All right, so here's an example of what we mean by that, or that kind of proves that concept. Two acids that have a very similar formula, HNO2 versus HNO3. And back in Gen Chem, you memorize that one of them is a strong acid, that's HNO3, that's nitric acid, HNO3. And the other one is a weak acid, HNO2 is a weak acid. It only partially ionizes. Well, we can explain why one of those, even though they're very similar, they're just different by one oxygen. We can use resonance and delocalization to explain why one is a weak acid and one is a strong acid. So here with the nitrous acid, HNO2, because it's a weak acid, remember we write it as a reversible reaction with water to give us the hydronium ion and the conjugate base, the NO2 minus, the nitrite. So you can do two resonance forms with nitrite, where you have the double bond between the nitrogen and the oxygen on the right, or between the nitrogen and the oxygen on the left. Those are the two resonance forms. Okay, well, what about nitric acid, which we said is a strong acid? So it's a one-directional arrow, reaction arrow. It's 100% reaction. It's a strong acid. Every time HNO3 encounters a H2O, it transforms into hydronium ion, H3O plus, and nitrate, NO3 minus. And that has three resonance forms, where that double bond sort of switches place in a formal sense between the nitrogen and the three different oxygens, okay? So we can say qualitatively that nitrate, NO3, has more resonance and therefore more delocalization than nitrite, NO2. It has an extra resonance forms. Its negative charge is delocalized even more than it is in NO2 minus. Okay, so fewer resonance forms are on the nitrite, so there's less delocalization. So it's a less stable ion. So the consequence is it's going to be a stronger conjugate base. Remember, stability, things that are stable don't react. They have no propensity to react. So if the nitrite is less stable, then it's going to be more reactive. And it's going to react in a way that, you know, it's a conjugate base. So it's going to do what bases do. It's going to take on a hydrogen, an H plus from like a water molecule. Well, it's just the opposite when you're talking about the nitrate, NO3 minus. It has more resonance forms. So it has more delocalization. So it's more stable, and therefore it's a weaker conjugate base. So that's why NO2 is associated with a weak acid, HNO2, and NO3 is associated with a strong acid, HNO3.